This tutorial is to translate the concept from to just talk into mathematical equations. There are two parts of this tutorial. First is about convolution. It may sound unfamiliar, but it is just a mathematical operation, like addition and division. For an age-structured population, convolution will do the job. However, we need a few more math tools to reduce the computation cost on a stage-structured population. I will get into it later in the tutorial. Let's imagine an age-structured population with only two age classes. Kappa is a probability distribution for the number of kids born by an individual. The component in Kappa 1 is probabilities to give 0, 1, 2, 3, and more kids at age class 1. Same for Kappa 2. Note that the mean of Kappa distribution is the fertility of the age class. Let's assume that an individual may produce 0, 1, or 2 kids at either age class, like it's shown under I1 and I2 in the figure. Then the lifetime reproductive success, the total number of kids produced during lifetime of the individual, may be 0, 1, 2, 3, and 4, like it's shown under N. There's only one way for an individual to get 0 kids during its lifetime. That is to give no birth at both ages. The path is marked by red arrows here. The probability of that is the product of probability of no birth at age 1 and probability of no birth at age 2, which is written here as delta 0 equals kappa 1, 0 times kappa 2, 0. There are two ways for an individual to get one kid during its lifetime. That is to give no birth at age 1 and 1 at age 2, or get 1 at age 1 and 0 at age 2. The paths are marked by orange arrows here. The probability of that sum of probabilities are those two paths, which are the products of the probabilities of 0 at age 1 and 1 at age 2, and 1 at age 1 and 0 at age 2, which is written here as delta 1 equals kappa 1, 0 times kappa 2, 1 plus kappa 1, 1 times kappa 2, 0. So delta n, the probability of n kids after two age classes, is the sum of all possible paths probabilities, which are the combination of the number of kids born at each age, as long as the sum is n. So if m1 kids are born at age 1, then nm1 are born at age 2. And the discrete convolution is just the right tool for this. Delta is the discrete convolution of the distributions kappa 1 and kappa 2. For an age-structured population, the distribution of the number of kids an individual survives to age has this repeat convolution of the distributions kappa 1, 2, 3 till kappa 8. So the lifetime reproductive success distribution of the population is the weighted sum of delta at all ages. The weight is the death distribution phi, which is the proportion of individuals that die at each age. It is the product of the probability of survival to the age and the probability of dying at the age. Stage-structured populations can use convolution to calculate the distribution as well. Kappa here is the probability of the number of kids at a given stage. The mean of kappa distribution here is the fertility of the stage class. As Tuja discussed in his talk, individuals can spend a long time in a stage before they move to another stage. We can repeat convolution for all the time steps till they die. As shown here, this can become computationally costly if we have many stages, and the individuals stay in a stage for a long time. Nicely, we found another math tool to reduce the computational cost. That is Fourier transform. Fourier transform is a math operation that uses the frequency domain to represent a function. Like we show here, kappa hat is the Fourier transform of kappa. Theta is the frequency. Different z's represent different frequencies. We can calculate a value for each frequency for kappa hat. So what good will this transform do? As we described, the lifetime reproductive success distribution is a long sequence of convolution for kappa at each stage. The beauty of Fourier transform is that the convolution of distributions is the product of their Fourier transform. So instead of computing convolution, we are computing much less costly operation production. So convolution and Fourier transform make the math simpler than it used to be. We also use other tricks such as the block method. They are just the right math operations for this problem. Nothing fancy. If you are interested in them, you can find the details in appendix of our 2020 LRS paper on ecology letters. Thank you for listening.